It's my pleasure to introduce Manuel Rivera from Purdue University, talking about the fundamental group and homotopy theory over a field.
Thank you. Thank you. So I think most of you have heard me talk about similar things, except maybe some. So if I say something without defining or something, just please stop me and let me know. But I'm going to try to be relatively self-contained again. Okay, so let me start by recalling the following classical theorems from algebraic topology. The first one is usually attributed to Whitehead, and it says that a map between simply connected spaces f from x to y is a weak homotopy equivalence, meaning that f induces an isomorphism on the homotopy groups, if and only if it is a homology equivalence with integral coefficients. Okay. And this follows from a more fundamental classical statement due to Hurewicz, which I'm going to state in the following form. The first non-zero homotopy and homology groups of a simply connected space occur in the same dimension and are naturally isomorphic. Okay. And I think of these two statements as lying at the bottom of fundamental work in algebraic topology. For example, it lies at the bottom of rational homotopy theory in the style of Sullivan and Quillen, p-adic homotopy theory in the style of Gors, Mendel, Chris, and other people. It's also the starting point in some sense of the theory of localization and completion of Bousfield and Kahn, and so on. So I'm going to talk about all of these today. I'm going to try to say something about it. So let me pose two questions. The first one is the following. So let X and Y be two simply connected spaces, and I will reformulate Whitehead's theorem slightly in the following form, which will be a little bit better for my purposes. So a map between simply connected spaces is a weak homotopy equivalence if and only if the induced map at the level of chains, of singular chains, is a quasi-isomorphism of chain complexes. So I can reformulate Whitehead in this form because I have a map between spaces. So by naturality, that induces a map at the level of chains, right? So saying that the induced map is a homology isomorphism is the same as saying that the induced map at the level of chains is a quasi-isomorphism, okay?
So you could have, theoretically, you could have a quasi-isomorphism between the chain complexes, and there's no weak homotopy equivalence between the spaces?
Yeah, correct. You need the map here. And I'm going to talk about, actually, that's the next question, question one, as I posted, see? Can we drop the map F to obtain a statement of the form the chains on X and the chains on Y are weakly equivalent under some notion of weak equivalence, if and only if X and Y are weakly homotopy equivalent? So that's the natural question, as Peter asked. And the answer is yes, we can, considering more algebraic structure. Okay, so over the rationals, this follows from rational homotopy theory, which tells us that using a different algebraic gadget, the rational piecewise linear differential forms on X and Y. So these are commutative differential graded algebras that you can associate to X and Y over the rationals. And the result is that these are quasi-isomorphic in the category of commutative differential graded algebras if and only if X and Y are rationally weakly equivalent. And there's no need for a map in this statement. However, I'm taking into account more structure at the chain level. right? I'm considering these commutative differential graded algebras of polynomial forms. And over the integers, Mike Mendel gave an answer to this question. Namely, he proved that he used the cochains, singular cochains on X and Y. So the singular cochains on X and Y are quasi-isomorphic as E-infinity algebras, if and only if X and Y are weakly homotopy equivalents. And in Mendel's statements, X and Y are assumed to be of finite type and simply connected, of course. I'm assuming simple connectivity in these two answers. So E-infinity algebra, so that means an E-infinity algebra is an algebra equipped with a hierarchy of homotopies controlling the failure of cocommutativity. So it's commutative up to an infinite family of homotopies. And if you consider this as part of your structure, then you get that the integral cochains considered as E-infinity algebras completely determine the homotopy type under these assumptions.
Are you I'm not super familiar with everything. So for any simply connected space, is the chains automatically an E-infinity algebra, or is this like, oh, you're assuming they have an E-infinity structure and
no. For any space, none. I mean, you don't need to assume simply connectedness or any assumption. Any space, you can consider the cochains, the singular cochains in the space. That's a strictly associative algebra, and it's commutative up to homotopy. And moreover, it's commutative up to an infinite family of homotopies. So okay. For any space, you can associate an E-infinity structure on the cochains naturally.
So you don't need anything like that your space has to be an infinite loop space or anything. It's automatic. Cool.
No. The cup product extends, the cup product at the level of singular cochains extends to an E-infinity algebra structure.
Thanks.
Yeah.
So my advisor described this as, Manuel's advisor is famous for saying taking homology is like taking a picture of your wife and sending her away. And then at one of his birthday conferences, my advisor said, but Mike Mendel proved you can recover your wife if you remember the E-infinity structure from the picture.
Exactly. Okay. Any other questions?
A quick question. So can one drop the finite type assumption if you work with chains instead of cochains?
Potentially, yes. I'm going to talk a little bit about that. But no one has done it yet because the homotopy theory of coalgebras is a little bit tricky. But today I'm going to make a statement without finite type over a field using chains, coalgebras of chains. Okay?
Okay.
But yeah, that's potentially one can do that. I mean, the finite type assumption has to do with dualizing from coalgebras to algebras. Yeah.
Right.
What else? Yeah. So I should say that in Sullivan's theory of rational homotopy theory, there's also a finite type assumption. However, in Quillen's theory, there is no finite type assumption because Quillen uses a differential graded cocommutative coalgebra to capture the rational homotopy theory of a space. So already in Quillen's theory, there's no finite type assumptions. Yeah. So the second question, what about non-simply connected spaces? First of all, can we extend Whitehead's theorem in some form to non-simply connected spaces? Remember, Whitehead's theorem was that a map between simply connected spaces is a homotopy equivalence if and only if it's a homology equivalence. And then can we answer the first question in this setting of non-simply connected spaces? Meaning, can we drop the map and determine the homotopy type for non-simply connected spaces? So the answer to the first question of extending Whitehead's theorem, so we proved a extension of Whitehead's theorem, which has the following form: a map between path-connected pointed spaces, F from X to Y, B and C are base points, and X and Y respectively, is a weak homotopy equivalence if and only if the induced map at the level of chains, of coalgebras of chains. So this B should be a C. I'm sorry, that's a typo. It's a cobar quasi-isomorphism. So let me explain what this means. So first of all, the singular chains on any space are have a natural differential graded coassociative coalgebra structure using the Alexander-Whitney construction. This dualizes to the cup product at the level of cochains. And by a cobar quasi-isomorphism, I mean the following. So a map between connected differential graded coassociative R coalgebras, R is an arbitrary ring here, is called a cobar quasi-isomorphism. If it becomes a quasi-isomorphism after applying the cobar function. I'm going to recall the definition of the cobar function in a minute. Let me remark that this is strictly stronger than being a quasi-isomorphism of coalgebras. Namely, every cobar quasi-isomorphism is a quasi-isomorphism, but not vice versa. So by strengthening the notion of weak equivalence on the algebraic side, where we are able to capture the information of the fundamental group of the spaces. That's the idea in this extension of Whitehead's theorem. And I'm going to outline the proof today. So there's another question that is, I stated. So here, can we answer question 1 in this setting? Meaning, can we drop this map F and we give an answer over a field. So for convenience, instead of using pointed spaces, I'm going to use reduced concomplex. So by reduced concomplex, I mean a concomplex with a single vertex. So given any pointed space, you can naturally associate a reduced concomplex by taking the singular complex, but now you require the vertices of every singular simplex to be identified at the base point. Anyway, that's just a technicality. So let me state what we prove, and I'm going to outline the proof of this theorem as well, hopefully. So the statement is the following. So for any field F, 2 reduced concomplexes, or you can think of these as pointed path-connected spaces, that's fine. 2 reduced concomplexes X and Y are pi1 F equivalent, a notion to be defined, if and only if the simplicial cocommutative coalgebras of chains fx and fy are Khobar quasi-isomorphic. So there's many things I should explain in this statement.
Sorry, can I ask something? So this is new, right? The other one you already talked about.
Yeah, this is new. Yeah.
This is the new one. Okay.
Yeah, we posted this this week.
Right. Yeah, I think I saw that.
Yeah. So yeah. So before I explain these notions, let me say that this is saying essentially that connected concomplexes are completely determined by their simplicial cocommutative coalgebras of chains over a field. So let me try to make precise what I mean by this. So first of all, what do I mean by pi1 F equivalence? So let's fix a commutative ring R, then a map of reduced concomplexes F from X to X prime is called a pi1 R equivalence if F induces an isomorphism of fundamental groups and F induces an R homology isomorphism at the level of universal covers. Namely, if the induced map F tilde at the level of universal covers becomes a homology isomorphism with R coefficients. That's a pi1 R equivalence. So let me say what I mean by this algebraic framework of simplicial cocommutative coalgebras. Okay. So a simplicial cocommutative coalgebra is a simplicial object in the category of cocommutative coalgebras. So it's a functor from the simplex category, the opposite of the simplex category, to the category of cocommutative R coalgebras. I'm going to assume all my coalgebras are co-unital and co-augmented, and yeah. So this is equivalent to a collection of coalgebras for any non-negative integer n of cocommutative coalgebras with phase and degeneracy maps, which are R coalgebra maps and satisfy the simplicial identities. That's a simplicial coalgebra.
Can you flip back one page? I want to just understand something. So what was the conditions? So basically, what are you doing? You're contracting the zero skeleton, and then you say you can go to the universal cover and then somehow contract the one skeleton. So that's what you're doing there. And then you separate out those two parts. Okay. Yeah. And then what is the R about? So that you need a field or something? So what do you need this?
So in the statement, I'm assuming R is a field, but I'm defining the notion for any commutative ring R. Okay. You'll see how I use the fact that.
Okay. Yeah. No. I just wanted to check which pieces you're looking at and how the theorem works. All right. Yeah. Thanks.
Yeah. Can you repeat what omega means? Omega quasi-isomorphic?
Yeah. So I haven't defined what omega is. I will do it in a second, but let me repeat it. So a map of So this notion is for differential graded coalgebras, and I'm considering a different kind of algebraic gadget, but it will give rise to a differential graded coalgebra. So a map of differential graded coalgebras is an omega quasi-isomorphism. If after I apply this functor, this cobar functor from coalgebras to algebras, it becomes a quasi-isomorphism of algebras on this side.
I see. Thanks. Yeah, I forgot about that already again.
Okay, I will keep repeating it during my talk, so it should be
highly appreciated by me.
Yeah. So pi1 R equivalence induces an isomorphism on fundamental groups and an R homology equivalence at the level of universal covers. Okay, so simplicial coalgebras are simplicial objects in the category of coalgebras. As an example, the main example that we will be considering is the simplicial coalgebra of chains. So what What do I mean by this? So if X is any simplicial set, then Rx will denote the simplicial coalgebra, which at level n is freely generated by the set of n simplices. And then the coproduct, each of these coproducts at level n is induced by the diagonal map. That's the simplicial coalgebra of chains attached to any simplicial sets. And this gives rise to a differential graded coalgebra, right? The one we are more familiar with as follows. So there's a normalized chains functor, which you also encounter in the Dalt-Hahn correspondence, right? From simplicial R modules to chain complexes, but now this has more structure. Namely, the normalized chains functor is a functor from the category of simplicial. Actually, you don't need the cocommutativity here. You can just say simplicial coassociative coalgebras to differential graded algebras. So normalized chains, by normalized chains, I mean the usual construction, right? Where you mod out by degenerate simplices, and then the differential becomes the alternating sum of the face maps. But now I'm saying that if you start with a simplicial coalgebra, the normalized chains have an induced graded coalgebra structure given by the Alexander-Whitney construction. Namely, if delta C denotes the coproduct of C, then you can consider the following composition, where AW denotes the Alexander-Whitney construction, and this gives a graded coalgebra structure on the normalized chains. Okay. So before I keep going, let me say that if C is the simplicial coalgebra of chains, as I explained, if C is the simplicial coalgebra of chains on a simplicial set, as I explained in my previous slide, then this normalized chains coalgebra is exactly the Alexander-Whitney differential graded coalgebra of chains we're used to working with, the one which dualizes to the cochains with cup product. So now let me say what I mean by a cobar quasi-isomorphism at the level of simplicial coalgebras. So a map G from C to C prime between simplicial cocommutative coalgebras is a Khobar quasi-isomorphism or omega quasi-isomorphism if the induced map at the level of differential graded coassociative coalgebras of normalized chains is a Khobar quasi-isomorphism in the previous sense I explained. Namely, if it becomes a quasi-isomorphism after applying the Khobar functor to these differential graded coassociative coalgebras. Okay, so that notion lifts to the world of simplicial coalgebras through this functor of normalized chains. And oh, this is the this is notation, but it's also the what I said before. The normalized chains on the simplicial coalgebra of R chains will be denoted by C star X comma R because it's exactly the chains on a simplicial set with R coefficients as we know it. Okay. So let me say something more about these pi1 R equivalences. So first, any pi1 R equivalence is an R homology equivalence. This is an exercise. I won't tell you guys, so you can try it or give it to your students. So remember, a pi1 R equivalence is a map which is an isomorphism on fundamental groups and a homology isomorphism on the universal covers with our coefficients. So I'm claiming that this implies that the map you started with induces a homology equivalence with our coefficients. So that's an exercise. Another fact, which kind of explains why this is a sensible notion or an interesting notion to study. A pi1 z equivalence is a homotopy equivalence, right? So
a weak homotopy equivalence?
Right, but I define pi1 z equivalence to be a map between concomplexes satisfying something. So a weak equivalence between concomplexes is a homotopy equivalence.
Thanks for that reminder. Yeah, good.
Yeah, yeah. So this is clear, right? Because it induces an isomorphism on pi1 on fundamental groups, and then an integral homology isomorphism at the universal covers. But universal covers are simply connected. So by Whitehead, a homology equivalence at the universal covers is the same as a homotopy equivalence at that level. So you get a map that induces an isomorphism on all homotopy groups. And another statement, which is I'm also going to leave as an exercise, is the fact that a map of concomplexes, F from X to Y, is a pi1 R equivalence if and only if it induces an isomorphism on fundamental groups and it induces an isomorphism on homology with coefficients on any local system M. So this has to do with the universality of the universal cover.
I guess this gives a hint for the exercise of number 1, huh?
Yeah, exactly. Yeah, definitely. It's kind of the same proof, actually. So, yeah. So these are pi1 R equivalences. So let me outline the proof of our theorem. Maybe let me quickly recall the statement again, now that you know I explained all the notions. So for any field F, two reduced complexes, X and Y, are pi1 F equivalent. That means they are connected by maps of concomplexes, each of which is a pi1 F equivalence. If and only if these algebraic gadgets associated to them, the simplicial cocommutative coalgebras of chains, are connected in the category of cocommutative coalgebras, of simplicial cocommutative coalgebras, by cobar quasi-isomorphisms. And this works over an arbitrary field F, namely over Fp and over the rationals. And these two are important, particularly important cases because we know that we have these arithmetic square argument that lets you relate the integers to FP completion and rationalization and so on. So,
quick question.
Yeah.
So you're saying that if you have homology isomorphism for every field, it doesn't imply integral isomorphism?
If you have, so let me make a statement. If you have a map of spaces which induces a homology isomorphism over any field, you do have an integral isomorphism, integral homology isomorphism. More precisely, if you have a map of spaces which induces an isomorphism on homology with coefficients on Fp for all primes P, and it induces an isomorphism on rational homology, then you get that the map induces an isomorphism on integral homology.
I see. So you can like use your theorem, just check those fields on one side and you get out homotopy.
Not yet, because the statement in this, the way I stated what I just said, assumes you have a map of spaces. See?
Oh.
I'm not assuming I have a map of spaces. I mean, in one direction, you could do it. If you have a, you know, like if X and Y are pi 1 F equivalent for any F, then you do get what you want at the level of algebraic.
Well, you do have a map for every F, but they don't have to be the same F, the same map. And
exactly.
you have to have the same map for every.
Exactly. You have a map for all F, but they don't have to be induced by the same map. Yeah.
Okay. And then maybe I missed it, but you said you now defined everything. I didn't hear you define what cobar is, or maybe I just missed that.
Yeah, I did, but I will go through it again. It's here. So, so connected means that at degree 0 is one copy of the underlying ring. So
but
a map.
You have again quasi omega quasi-isomorphism. What does that mean?
It means this: a map between simplicial coalgebras, cocommutative coalgebras, is an omega quasi-isomorphism. I'm defining what this means. If the induced map at the level of differential graded coalgebras, given induced by this normalized chains functor, is a Khobar quasi-isomorphism or omega quasi-isomorphism in the previous sense I described.
What was the previous sense then?
The previous sense is that if you apply this Khobar functor to this map here, NG.
What's the Khobar functor? That's what I'm asking.
The definition of the Khobar functor is what you want?
Yes.
I will define it in my next slide. Yeah.
Okay, so that was all. I thought I missed that because you said you defined everything now that was in the theorem, but you didn't define the Khobar functor yet. Okay, good.
Okay, good. I agree. Yeah, I will define the Khobar functor explicitly. Okay. Any other questions?
Do you have actual examples where two spaces are pi 1 F equivalent over every field, but not over Z?
No, because I think I can still prove this statement. Okay. I mean, I think there are other techniques. I mean, what Peter suggested does not apply immediately because you don't have this map, but there are other techniques that were put forward by Sullivan regarding, I don't know if you've heard the fracture theorems, which says that you can recover a space from its P completions and its rationalizations in some way. So there are other techniques that should lead to an integral statement of the one you just said. Yeah. Okay. So that's my final conjecture will be that this holds over the integers, and we've proven certain cases already. So under some assumptions. Yeah. Okay. So before defining the Khobar functor, sorry, Peter, let me outline the proof. I think maybe the slide with the definition of the Khobar functor should have come before, but whatever. Let me outline the proof to give you an idea of how this would go. So first of all, if X is any Kahn complex with a single vertex, a reduced Kahn complex. So the first observation, which is non-trivial and quite interesting, and I think I've talked about this in my earlier talks already, is that the fundamental group of X, of any space X you can think, is completely determined by certain quadratic equation on the zeroth homology of the Khobar construction of this coalgebra of chains. In other words, the fundamental group of a space is completely determined by the algebraic structure of the chains over any coefficient ring R, even a field. That's kind of a cool observation, which I will go over it again. second part of the proof is that the simplicial coalgebra on the universal cover of X is completely determined by the simplicial cocommutative coalgebra on X. Namely, there's an algebraic construction you can apply to any abstract simplicial coalgebra that produces the universal cover. Then all of these constructions will be invariant with respect to Khobar quasi-isomorphisms. And finally, we use a result of Paul Gore's. I missed an S here. Gore's has two S's, which says that for any field F, simplicial sets Z and Y are F equivalent if and only if the simplicial coalgebras of F chains are quasi-isomorphic. So F equivalent means an F equivalence. Oh, here it is. So more generally, for any R, a map is an R equivalence if it induces an isomorphism on homology with R coefficients. So this statement of Gore's, it's kind of an extension of rational homotopy theory for any field. So for example, if you assume that if F is the rationals and you assume that Z and Y are simply connected, then you obtain a similar statement to that of rational homotopy theory. Because rationally equivalent spaces, simply connected spaces, is the same as saying that your spaces have the same rational homotopy groups. And the idea is to apply this result of Gore's at the level of universal covers. So we start with the chains on X and the chains on Y, and we assume that they are cobar quasi-isomorphic. And then we pass to the universal covers. We get that the universal covers are quasi-isomorphic, and we use Gore's statements there. So that's kind of a rough outline. Okay, so now finally, the Khobar construction. Let me define it in detail. So suppose you have a differential graded coalgebra. The zero here means that the coalgebra is connected. So it means that C0 is one-dimensional. It's isomorphic to a single copy of R. So this D is the differential and this delta is the coproduct. So I want to define a differential graded algebra called omega of C as follows. So C bar is just, you first kill the 0th degree part of C, and then you shift it down by 1, everything. So everything that was in degree 1 becomes of degree 0, and so on. So that's C bar. And then I take the free algebra on C bar. That's what T C bar means. So these are monomials on C bar, right? Non-commutative monomials, the free algebra. And that has a product by just concatenating monomials. And now I want to define a differential on this free algebra. So the differential is defined as follows. So first, let me define it on C bar, namely on monomials of length 1. And then I will extend it as a derivation to monomials of arbitrary lengths. So on any element of C bar, X, define D to be, you first apply the differential of C to X with a sign here, plus the coproduct of C applied to X. So the differential will land again in C bar, and the coproduct will land in C bar tensor C bar. But this sum can be regarded as living inside the tensor algebra, right? It's just a monomial of length 1 plus a monomial of length 2. And now you just extend by Leibniz rule to monomials of arbitrary length. And you get a well-defined map from the free algebra to itself. That's the Khobar construction. It takes a differential graded coalgebra and it produces a differential graded algebra. And now the fact that the coproduct is co-associative, the differential of the underlying coalgebra squares to 0, and the fact that the coproduct and the differential are compatible, namely we started with a differential graded coalgebra, together imply that the square of this map is 0. So it's indeed a differential.
I guess I have to trust you on that, but it seems like in degree 4 there would be something, but I mean, maybe I just misunderstand how to apply Leibniz rule, and if I would sit down, I'd probably see that.
So I mean, do you understand what I mean by Leibniz rule? You have a monomial, and you just apply it to the first term, and then take the sum by applying it to the second term, and then add the term that you get when you apply that differential to the third term, and so on.
Yeah, but
and then this is an easy check, the fact that d squared equals 0, using these things I just stated here. I mean,
so you don't get anything in degree 4. You only get something in degree 3, because you don't apply the diagonal to both things at once. You only apply it to one at a time. I see.
Yeah.
Okay, that makes more sense then. Thanks.
Yeah. Okay, and now let me repeat once more. I'm going to go fast here because I've said it many times. There are two notions of weak equivalence between differential graded coalgebras. The first one is a map is a quasi-isomorphism if it induces an isomorphism on homology. The second one, which I've been repeating, is Khobar quasi-isomorphism, right? Which is a map of differential graded connected coalgebras is a Khobar quasi-isomorphism if it induces a quasi-isomorphism of differential graded algebras after applying the Khobar functor. And the claim is that this notion of Khobar quasi-isomorphism is strictly stronger than quasi-isomorphisms. However, the two notions agree when restricted to simply connected differential graded coalgebras, namely when restricted to differential graded coalgebras such that at the level 0 you have a single copy of the underlying ring, and at level 1 they're trivial. So this means isomorphic, not, this symbol. Okay, so now if X is actually any simplicial set, you can consider the chains on X with coefficients in R, right? And then that's a coalgebra with the Alexander-Whitney coproduct, and you can consider its Khobar construction. And I think it was Bowes was the first to describe this structure. There exists a coproduct on the Khobar construction of the coalgebra of chains on a space, which makes it a differential graded bialgebra. So the Khobar construction is an algebra. And I'm claiming you can construct a natural coproduct, making this algebra a bialgebra, namely that this coproduct map is a map of algebras, which models the chains on the base loop space of X. So the base loop space on X, by the base loop space on X, I mean Moore loops. So it's a strictly associative topological monoid obtained by concatenating loops. So if you take chains on the base loop space, that concatenation of loops induces an algebra structure. But since all chains on any space is a coalgebra structure, you also get a coproduct. And these are compatible, right? They give a bialgebra structure here. And the claim is that, in fact, for any connected, for any reduced concomplex X, the claim is that this bialgebra, the Khobar construction of the chains, models the chains on the base loop space as a bialgebra. Namely, there's a quasi-isomorphism. There's a natural quasi-isomorphism from the Khobar construction on the chains to the chains on the base loop space, which is compatible with these algebraic structures. So this coproduct is actually, so this is a useless comment, but let me just say it. It's determined by maps nabla PQ, where nabla PQ is a map on on the monomials of length 1 in the Khobar construction, and then it lands in this tensor product of P copies of the coalgebra tensor with Q copies of the coalgebra. You can just project on the right-hand side to obtain all of these components, and all of these components determine the map nabla. And I'm just saying this because this map nabla is induced by the E2 structure of the chains. So these maps here are part of the E2 coalgebra structure maps of the chains. But if you, I'm not going to use this fact. So the fact that this Khobar construction as a bialgebra models the base loop space implies that the zeroth homology of the Khobar construction is isomorphic to, in fact, the zeroth homology of the base loop space, which is the fundamental group ring of the space X. So pi 1 of X is a group, and then R of pi 1 of X is a group ring, and this is an isomorphism of bialgebras. In fact, it's an isomorphism of Hopf algebras, because this bialgebra has the property of being a Hopf algebra, namely it admits this antipode map. And now, under the assumption that R is an integral domain, which we should assume all the time in this talk, it turns out that the elements in this zeroth homology of the Khobar construction, which satisfy this quadratic equation, where nabla is the map induced by this coproduct, form a group, and moreover, this group is isomorphic to the fundamental group. I'm just applying the group-like elements functor to this bialgebra here. And when I do that, I obtain the fundamental group. So this is just an explanation of the fact that the algebraic structure of the chains on any space determines the fundamental group through this process.
Manuel, your time is running out.
I know, and I have a lot of slides, but I can go faster and try to summarize now.
Yeah, so, maybe two more minutes or something.
Yeah. Okay. So I'm going to skip this. So the idea is that given any connected simplicial cocommutative coalgebra, which might not come from a space, you can still define this coproduct on the Khobar construction of the chains of that coalgebra. And that tells us that we can associate to any simplicial coalgebra some kind of bialgebra, which plays the role of the fundamental group ring, which is essentially the zeroth homology of the Khobar construction of the chains in C. And so as a statement is that, a first statement is that if X and Y are concomplexes, then any zigzag of quasi-isomorphism, of Khobar quasi-isomorphisms between the simplicial cocommutative coalgebras of chains induces an isomorphism of fundamental groups. You can just apply this construction of taking the Khobar construction, a zeroth homology, and then group-like elements to every term in this zigzag. And at the endpoints, you get the fundamental groups. So that gives the first part of the proposition of the statement that I stated at the beginning that says that a zigzag of Khobar quasi-isomorphisms gives you a pi1 F equivalence in the case of a field. But here we can do it for any ring R, just obtaining the fundamental group. And let me skip this quickly. So now I can outline the extension of Whitehead's theorem. So hopefully we get this, I can get this point across in the last few minutes or 2 minutes. And the statement is that any map of reduced concomplexes is a weak homotopy equivalence if and only if the induced map at the level of integral chains is a Khobar quasi-isomorphism. So if you have a map of the coalgebras of chains, you get a map between an isomorphism between the zeroth homology of the Khobar constructions, because I was assuming this map is a Khobar quasi-isomorphism, and that leads to a map of fundamental groups. And then I have to look at the universal covers now. And this follows from the following statement. If M is any local system, namely any Z pi1 module, then the fact that the induced map at the level of chains is a Khobar quasi-isomorphism implies that the map at the level of chains with local coefficients is a quasi-isomorphism. So this follows from some homological algebra. And when M is the group ring itself with the multiplication as the action, you get a quasi-isomorphism between the universal covers. And that kind of does this, that's the outline for this extension of Whitehead's theorem. So let me skip this. And so I can stop here, but I have, if I can get a few more minutes, I would like to outline the proof of the final theorem using the ideas I've mentioned so far.
What does everybody else think about that?
Maybe 3
I'd be
minutes,
interested in that.
4 minutes?
That's fine.
Yeah.
That's
okay.
fine.
Okay, good. So now over a field F. Yeah. So the statement again, and there's the new statement, is the following. Two reduced concomplex X and Y are pi1 F equivalents, meaning they're connected by a zigzag of map of spaces, each of which is a pi1 F equivalence. Recall that a pi1 F equivalence is a map that induces an isomorphism on fundamental groups and an isomorphism on F homology at the universal covers. If and only if the connected simplicial cocommutative coalgebras of chains F of X and F of Y are Khobar quasi-isomorphic. So what's the idea? So let me outline the proof of one direction, the quote unquote harder one. So suppose you have a zigzag of Khobar quasi-isomorphisms between the chains. So the point is that these maps might not come from a map of spaces, right? It's an equivalence in certain homotopy category of algebraic objects, right? So you have this zigzag here. All the objects in this zigzag are simplicial commutative coalgebras, and all the maps are these cobar quasi-isomorphisms. So first of all, this induces an isomorphism on fundamental groups. That follows from the statements I described before. And the idea is that given any simplicial coalgebra, we can construct algebraically a universal cover that's a new simplicial commutative coalgebra, which mirrors the passage from the chains on a space to the chains on its universal cover. But it's purely algebraic. And if your maps were cobar quasi-isomorphisms, this construction is designed such that when you pass to these algebraic universal covers, you get quasi-isomorphisms. And it turns out that, I mean, the construction is defined such that at the endpoints, you will exactly get the simplicial coalgebra of chains on the universal cover of your space. And moreover, all of these objects in this new zigzag of universal covers by construction will be modules over, they have a pi1 action, and all of these maps will be equivariant. So now I use the work of Paul Gowers, which is this extension of rational homotopy theory for arbitrary fields, to conclude that the universal covers are pi1 equivariantly F equivalent, namely they're connected by maps which induce an isomorphism on homology with F coefficients. And this uses the assumption of a field, of the coefficient ring being a field, okay? And once I have this, I can take Borel constructions to make those actions free, and then take quotients, and I get my desired zigzag of Kahn complexes where each map is a pi1 F equivalence. So that's kind of the outline of that new theorem I wanted to share. And let me end up with this conjecture, which is that there should be similar statements integrally, and which say that the integral coalgebras of chains completely determine homotopy types, where the notion of equivalence in the algebraic side uses this Khobar quasi-isomorphism. And we should be able to use the statements over a field and the fracture theorems and arithmetic square arguments to prove this integral statement. Anyway, that's all I wanted to say. I know this was fast and I jumped a lot. Just let me know if you have any questions.
Thank you, Manuel. Are there questions?
Is there like any like Lie infinity
No.
thing that should know about the homotopy type?
No, no, not in the connected case. And we prove that there is no Lie infinity type thing. It's a bit tricky to explain now, but we prove there is no Lie algebra extending the one from rational homotopy theory, which determines the integral homotopy type. It's a cool statement, actually. Yeah.
So if there are no more questions, let's thank Manuel for his talk. And yeah.